Deep within the cosmos, an invisible architecture shapes everything we see. These are not mere voids but quantum shadows, the universe's most elusive components. By the end, you will see the cosmos through an entirely new lens, understanding the hidden forces that may govern its grandest designs. We will explore why galaxies spin too fast and what seeded the vast cosmic web in the first place. How much of reality remains just beyond our sight? A shadow on a wall is a simple absence of light, but a quantum shadow is something far more profound. It is not an emptiness but a vibrant, seething activity at the smallest scales of reality. Think of the vacuum of space not as a true void, but as a restless ocean. At any given moment, pairs of particles and their antimatter counterparts are constantly flickering into existence, borrowing energy from the universe before annihilating each other almost instantly. These are quantum fluctuations, and their brief, ghostly imprints are what we call quantum shadows. They are the universe's hidden background activity, a probabilistic dance of what could be, rather than what definitively is. This differs completely from a classical shadow, which is static and local. A quantum shadow is dynamic, non-local, meaning its influence can be connected across vast distances in an instant, and it is fundamentally probabilistic. We cannot say for certain a particle will appear, only that there is a probability it might. The great physicist Carlo Rovelli has suggested these are not mere mathematical curiosities, but dynamic entities that form the very fabric of spacetime. How can we possibly detect such ephemeral things? One of the most compelling clues comes from a lab experiment you can actually measure, known as the Casimir Effect. When you place two incredibly smooth metal plates extremely close together in a vacuum, something strange happens. The gap between the plates is so small that only certain wavelengths of those quantum fluctuations can fit. Outside the plates, a wider variety of fluctuations can exist. This difference in pressure from the seething quantum sea outside pushes the plates together with a faint, but measurable, force. It is a direct signature of the shadow world's activity. If these shadows are everywhere, exerting forces and shaping the vacuum itself, what are they truly made of? Are they just particles that almost were, or could they be something else entirely? This faint push between metal plates confirms the quantum shadows are real, yet their true nature remains one of the cosmos's most profound puzzles. The second great riddle asks a deceptively simple question. What are these shadows actually made of? Are they composed of unknown, exotic particles, or are they something even stranger, an emergent property of spacetime itself? This composition conundrum lies at the very heart of the dark matter mystery. For decades, we have known that galaxies rotate so fast they should fly apart. Something invisible with immense gravity must be holding them together. That something is dark matter, and quantum shadows are a prime theoretical candidate for its identity. One possibility is that these shadows are made of hypothetical particles like axions. These are not like the protons and electrons we know. Axions would be incredibly light and ghostly, trillions of times less massive than an electron, and they would interact with ordinary matter only through the most feeble of forces, passing through our entire planet as if it were not even there. Their existence would solve other puzzles in particle physics, making them an elegant, if elusive, solution. But other theories go even further. Insights from string theory propose that quantum shadows are not particles at all, but the vibrations of cosmic strings. Think of spacetime not as a smooth fabric, but as a vast, cosmic piano. The strings are incredibly dense, thread-like flaws in spacetime, and when they vibrate, they do not produce sound, but rather create the ghostly imprints we perceive as shadows. The variety of theoretical models is staggering. Supersymmetry suggests every known particle has a hidden superpartner, and the lightest of these could be the shadow substance that fills the cosmos. Loop quantum gravity, meanwhile, paints a picture where spacetime itself is woven from tiny, discrete loops, and the shadows are the collective hum of this fundamental structure. The challenge in detecting such components is immense. How do you find something that interacts with your detectors almost not at all? Their influence is so weak that they pass through our most sensitive instruments completely unnoticed. Yet we might be seeing their effects on a grand scale. Look at gravitational lensing, where the gravity of a massive object, like a galaxy cluster, bends the light from objects behind it. Sometimes we see tiny, anomalous distortions in that light, small warps that cannot be explained by the visible matter alone. These could be the subtle fingerprints of a dense cloud of quantum shadows, their collective gravity gently twisting the fabric of reality. Could it be that our entire universe is permeated by a shadow substance we cannot see? A vast, unseen ocean in which the islands of visible matter float. This silent, pervasive presence would not merely be a component of the cosmos. It would be its dominant feature, its gravitational hand quietly sculpting everything from the largest galactic clusters to the very fate of the universe. Galaxies spin with a speed that defies all logic. The outer stars race around the galactic center so fast that the immense gravity from all the visible stars, gas, and dust should not be enough to hold them in place. According to the laws of physics as we understand them, these galaxies should have torn themselves apart long ago. The astronomer Vera Rubin provided the definitive evidence for this enigma, her observations revealing a stark discrepancy between what we see and what gravity demands. There must be something more, a hidden source of gravity binding these cosmic pinwheels together. This is the central clue pointing to dark matter, and it forms the core of our third great riddle. How do quantum shadows interact with gravity, and could their invisible mass be the solution? The most straightforward idea is that these shadow particles, while not interacting with light, do possess mass. Their collective gravitational pull would then create an unseen scaffold, a vast spherical halo enveloping each galaxy, which guides the stars in their unexpectedly swift orbits. This is not the only theory, of course. Some scientists have proposed that our understanding of gravity itself is incomplete, leading to ideas like modified Newtonian dynamics, or MIND, which tweaks the laws of physics to explain the rotations without invisible matter. Yet the shadow hypothesis gains compelling support from cosmic collisions, most famously the bullet cluster. When two galaxy clusters smash through one another, the hot, visible gas, which comprises most of the normal matter, slowed down and pooled in the center from the drag. But something else, something invisible, kept right on moving. We know this because its immense gravity warped the light from background galaxies, creating a ghostly map of its location. That map showed the dark matter had sailed far ahead of the visible gas, almost as if it had passed right through the collision unscathed. This is precisely how a cloud of quantum shadows would behave, barely interacting with anything, even other matter, yet still bending space with its gravity. So if these shadows do gravitate, how do they congregate? They will be drawn to the same primordial wells of gravity that collected normal matter after the Big Bang, pooling into vast, diffuse clouds that form the gravitational backbone of every galaxy and cluster we see. Their silent, pervasive pull would be the unseen hand that sculpts the cosmos itself. The universe began not with a quiet whisper, but with a roar of pure energy. Yet when we look at the afterglow of that birth, the cosmic microwave background, we find it is not perfectly smooth. It is a tapestry of minute temperature differences, tiny ripples in the fabric of the newborn cosmos. These faint imperfections are the cosmic blueprints for everything we see today, the subtle seeds from which all structure would grow. Our fourth riddle asks a profound question. Did quantum shadows provide these very seeds, acting as the primordial architects for the first galaxies and the vast cosmic web? The theory of cosmic inflation provides a compelling mechanism. In the first fleeting fraction of a second, the universe underwent a period of exponential expansion, stretching a subatomic volume to a size larger than the observable cosmos. During this violent growth spurt, the microscopic quantum fluctuations, those shadows of what could be, were stretched to astronomical proportions. What was once a tiny probabilistic dance on the quantum scale became imprinted across the entire sky as variations in density. These shadows became the gravitational wells where matter would eventually begin to collect. Think of a perfectly still, smooth pond. If you were to sprinkle a fine dust across its surface, the dust would float randomly. But if you create a series of tiny, gentle depressions in the water, the dust will naturally drift into those low points, clumping together. In this analogy, the quantum shadows are the creators of those initial depressions in the fabric of space-time. The result of this process is a universe that evolves with a specific, intricate pattern. Computer simulations of cosmic evolution are a powerful test. When physicists run models that only include the gravity from normal matter, the universe that forms looks nothing like our own. Galaxies are sparse, and the large-scale structure is weak. But when they add a dark matter component that behaves precisely as we expect quantum shadows to behave, cold and weakly interacting, the simulation changes dramatically. A vast cosmic web emerges, a labyrinth of dark matter filaments connecting dense nodes where galaxies and clusters form. This digital universe looks remarkably like the one we observe through our telescopes, a universe threaded by an invisible skeleton. The grand, spiderweb-like pattern of galaxies we see mapped across the sky is perhaps the most stunning evidence of these initial seeds. It is the ghostly imprint of those amplified quantum shadows, their gravitational pull guiding the flow of matter for billions of years. It forces us to ask a humbling question. Without these unseen architects, would the universe be a formless, dark sea of scattered gas and stars? Could our galaxy, our solar system, even we ourselves, exist without the subtle, guiding hand of quantum shadows in the first moments of time? To answer that, we must trace their influence not just across space, but through the entire history of the cosmos. The birth of the universe was a realm of pure potential, a seething cauldron where the very concepts of space and time were not yet set. In that first incomprehensibly brief moment, known as the Planck epoch, the cosmos was so small and energetic that gravity itself was a quantum force, fluctuating wildly alongside all others. It is in this primordial forge that many cosmologists believe quantum shadows were born. Stephen Hawking and others theorized that the distinction between a particle and its shadow would have been blurred, with reality itself existing in a superposed state of all possibilities. These were not shadows cast by anything, but the fundamental flickers of existence from which everything else would condense. As the universe expanded and cooled, it passed through distinct cosmic epochs, and the shadows evolved with it. During the violent period of inflation, those initial microscopic fluctuations were stretched into the macroscopic density, variations that seeded all future structure. Then came the era of recombination, about 380,000 years after the Big Bang. This was when the universe cooled enough for electrons and protons to combine into neutral atoms, suddenly allowing light or photons to travel freely for the first time. This released the cosmic microwave background radiation we observe today. But what role did the shadows play? Their gravitational pull would have subtly sculpted the plasma, creating the slight over densities and under densities that are frozen into that ancient light. The patterns we see in that afterglow are a direct imprint of the shadowy scaffolding already in place. This evolutionary journey suggests a dynamic life for these entities. Were they a constant, unchanging presence from the first instant, or did their nature and influence shift as the cosmos matured? Did they cool and slow down, becoming the cold dark matter that governs galaxies today? Or could some component have decayed or transformed into other forms of energy? The timeline of their existence is not just a historical curiosity. It forces us to ask if the rules governing these shadows have remained the same for 14 billion years, or if the hidden architecture of reality is itself a story of cosmic evolution. This very question of their constancy leads directly to the next great puzzle. If they have changed over time, are they truly the same in every corner of the void? Or could their distribution hold even deeper secrets? The cosmos presents us with a profound contradiction. On the grandest scales, the universe appears remarkably uniform, a principle known as homogeneity and isotropy. Every vast region of space looks statistically the same as every other, a sea of galaxies with no central point or preferred direction. This smoothness is etched into the cosmic microwave background, the ancient light from the infant universe, which shows only tiny temperature variations across the entire sky. Yet, when we map the universe today, we see a wildly different story. Galaxies are not scattered evenly. They are gathered into immense clusters, long filaments, and vast, empty voids, forming a cosmic web. This entire structure is believed to be woven upon the gravitational skeleton of dark matter, a substance that is clearly and powerfully clumped. So we arrive at the sixth riddle. Why do quantum shadows, the prime candidates for this dark matter, appear so uniform in one context and so distinctly clumped in another? How can the same entity be both the source of cosmic smoothness and cosmic lumpiness? The answer may lie in the subtle ways these shadows interact, or more precisely, how they avoid interacting. The initial uniformity comes from their origin story. Born from quantum fluctuations stretched across the cosmos during inflation, they were imprinted with a nearly identical distribution everywhere. They started smooth. But gravity is a patient sculptor. Over billions of years, even the tiniest overdensities in this shadow sea began to pull in more shadows. If these entities do not interact with each other, if they are what physicists call collisionless, they can simply fall into these gravitational wells and stay there, piling up to form the dense halos we infer around galaxies. They pass right through one another, allowing for extreme clumping. But what if some quantum shadows do interact, just very weakly? This is the theory of self-interacting dark matter. Imagine a crowded room where everyone is a ghost. If the ghosts cannot touch each other, they can all collapse into one corner, an extreme clump. But if they have very faint, repulsive forces between them, they would maintain a bit more personal space, leading to a smoother, more spread-out distribution within the halo. This could solve several small-scale puzzles about the structure of galaxies. The large-scale surveys, like the Sloan Digital Sky Survey, reveal this dual nature perfectly. They show the breathtaking cosmic web, the ultimate expression of clumping. But they also confirm that if you zoom out far enough, the average density of the universe is the same everywhere. The shadows are both smoothly distributed in the background and intensely clumped within the web's strands and nodes. Consider the great cosmic voids, the empty deserts between the web's filaments. These regions are not completely devoid of quantum shadows, but they are far less dense. The shadows have seemingly drained away, flowing toward the denser regions under gravity's pull. Their distribution is not random. It is a detailed map of the universe's gravitational history. What invisible forces, then, truly govern where these shadows congregate? Is it gravity alone, or do the shadows themselves possess a hidden social life, a capacity to interact in ways we have yet to fathom? Their silent nature raises a critical question for our seventh riddle. Do quantum shadows interact at all with the known particles of our world, the photons and neutrinos that make up the standard model of physics? We know they do not emit light, for they are shadows, but perhaps they scatter or absorb it with an almost unimaginable weakness. This is not a search for something that shouts its presence, but for a whisper so faint it borders on silence. Deep underground, in laboratories shielded from cosmic rays, experiments like Xenon 1T are listening for that whisper. These detectors use vast vats of ultra-pure liquid xenon, waiting for the minuscule flash of light or charge that would occur if a dark matter particle, a potential quantum shadow, were to bump into a xenon nucleus. It is like trying to hear a single snowflake land on a quiet field during a blizzard. The physicist Elena April, a leader in this field, has described the effort as pushing detection to its absolute limits, probing for interactions billions of times weaker than those of the familiar weak nuclear force. So far, the results have been null, a profound silence that tells us just how ghostly these entities must be. But how could such an interaction even occur? Theoretical models propose the existence of hidden sectors, entire families of particles and forces that operate parallel to our own, almost completely detached. The only connection between our world and this shadow realm might be through a tiny, fragile portal, a hypothetical particle or field that acts as a mediator. This portal would allow for a minuscule probability of interaction, a chance in countless trillions that a shadow might nudge a known particle. One of the most tantalizing hints of this comes not from a direct detection, but from a seasonal rhythm. Some experiments have searched for an annual modulation in their signal. The idea is that as Earth moves around the Sun, our planet's velocity through the galactic dark matter halo changes. In June, we are moving head first into the halo, and in December, we are moving with it. This should cause a tiny increase in the apparent wind of dark matter particles in summer, leading to a few more potential interactions. Observing such a pattern would be a spectacular confirmation. Yet even these subtle searches have yielded ambiguous or null results. If these shadows do interact, why is their touch so incredibly feeble? It may be that the mediating portal is incredibly massive, making the interaction incredibly unlikely, or that the force carrier itself is exceptionally weak. This profound elusiveness forces physicists to think far beyond traditional methods. They are now designing experiments that look not for a nuclear recoil, but for other, even subtler effects. What if the shadow's passage causes a tiny distortion in an electromagnetic field, or leaves a trace in the quantum spin of an atom? The search is evolving from listening for a bump in the night to sensing the faintest possible displacement of air. If they are this difficult to find through force, perhaps we should look for them not by what they do, but by what they are made of. Could their substance be something entirely outside our current understanding of matter? Trying to see a shadow in a completely dark room is a perfect metaphor for this hunt. You are searching for an absence of light against a background of absolute blackness. This is the eighth riddle, a monumental challenge in detection. How do you measure something defined by its elusiveness, an entity that barely touches our reality? The quest demands technologies of almost impossible sensitivity. Consider the Laser Interferometer Gravitational Wave Observatory, or LIGO. It detected ripples in spacetime so minute that they shift its 4-kilometer-long arms by a distance 10,000 times smaller than a proton. This is the level of precision we are chasing. Researchers are now pushing into even more exotic territory with quantum sensors. These devices leverage the bizarre rules of the quantum world themselves. Some use clouds of atoms cooled to near absolute zero. At these temperatures, the atoms behave less like particles and more like waves, becoming exquisitely sensitive to the faintest gravitational tugs or energy shifts a passing quantum shadow might impart. Others employ superconductors, materials that carry electrical current with zero resistance, forming a perfect quantum state that could be disrupted by the most subtle of influences. The problem is the noise. Every detection attempt is buried under a cacophony of background signals. Cosmic rays from deep space, the faint natural radioactivity from the rocks surrounding an underground lab, Even the quantum jitter of atoms at room temperature all create a deafening roar that can completely mask the faint whisper of a shadow interaction. This is the noise floor, and the entire goal of experimental design is to push that floor as low as humanly possible. Upcoming projects are being built with this singular purpose. The Laser Interferometer Space Antenna, or LISA, will be a gravitational wave observatory in space, free from the seismic rumble of Earth, potentially sensitive enough to hear the collective hum of countless shadows. The Darwin Project envisions a next-generation liquid xenon detector, so massive and pure that it could finally hear a signal rise above the statistical background. Perhaps the most profound path forward uses the shadow's own quantum nature against it. Experiments are now exploring whether the phenomenon of quantum entanglement could serve as a probe. If two particles are entangled, their fates are linked instantaneously across any distance. The theory suggests that a dense cloud of quantum shadows, with its immense gravitational field, could subtly decohere this entanglement, causing the particles to lose their magical connection faster than expected. It would be an indirect fingerprint, not of a single shadow, but of their collective gravitational presence. This leads to a deeply reflective question for the entire field. Will we ever observe a quantum shadow directly? Or are they destined to remain forever in the realm of theoretical inference, known only by their gravitational effects on the cosmos? The answer may force us to reconsider the very foundations of what we mean by observation. If these entities are as fundamental as the fabric of space-time, our very concept of direct detection might need to evolve. We are left to wonder if the final proof will not be a single, triumphant signal in a detector, but a gradual convergence of evidence from the cosmos, from particle colliders, and from the quantum lab, painting an inescapable picture of a reality perpetually half in shadow. Our current map of reality, the standard model of particle physics, is a triumph of human intellect. It catalogs the known particles and three of the fundamental forces with breathtaking precision. Yet it contains a profound and silent omission. It offers no candidate for the quantum shadows that appear to dominate the cosmos, and it remains completely silent on the nature of gravity. This is the ninth riddle. Which theoretical framework can truly accommodate these shadows, and does their existence demand a complete rewriting of our physical laws? General relativity, Einstein's masterpiece, describes gravity as the curvature of spacetime by matter and energy. It is a classical theory, a smooth, deterministic landscape. Quantum shadows, with their probabilistic, flickering nature, do not fit neatly into this picture. The two foundational pillars of modern physics are fundamentally at odds, and quantum shadows are caught directly in the crossfire. To resolve this, physicists have proposed radical extensions of reality. String theory suggests that the fundamental constituents of the universe are not point-like particles, but tiny, vibrating strings and membranes. The different vibrations of these strings correspond to different particles, including, potentially, the ghostly constituents of quantum shadows. In this framework, a shadow could be a specific, stable vibrational mode of a string, one that does not interact with light. The theory naturally incorporates gravity and even proposes a staggering concept known as the holographic principle, explored through the AD-S/CFT correspondence. This idea suggests that our three-dimensional reality, including the quantum shadows within it, might be a projection from information stored on a two-dimensional surface at its boundary. The shadows we perceive would be a holographic illusion of a deeper reality. A competing vision comes from loop quantum gravity. Theorist Lee Smolin has championed this approach, which emphasizes background independence. This means the theory does not describe particles moving on a pre-existing stage of spacetime. Instead, space and time themselves are woven from a network of discrete, interconnected loops. In this view, quantum shadows are not things within space, but excitations of space itself. They are the knots and weaves in the fundamental fabric of the cosmos. Then there are ideas like emergent gravity, which propose that gravity is not a fundamental force at all, but a side effect of the collective behavior of microscopic quantum bits, much like temperature emerges from the jostling of atoms. In this picture, quantum shadows would be the underlying microscopic constituents, and the phenomena we attribute to dark matter would be a consequence of our incomplete understanding of how gravity emerges from this deeper layer. Comparing these frameworks reveals a stark philosophical divide. String theory often requires extra dimensions of space to be mathematically consistent, while loop quantum gravity strives to describe our familiar 4 dimensions from the ground up. Their predictions for the precise behavior of quantum shadows differ subtly. For instance, would a cloud of string, theoretic shadows behave identically to a condensate of spacetime loops in the extreme gravity near a black hole? We do not yet know. The search for a single, unified theory of quantum gravity is, in many ways, the search for the true nature of these shadows. Does their explanation absolutely require a theory of everything, a final set of equations that binds all forces and particles into one coherent whole? Or could they be understood within a more limited, but still revolutionary, framework? The answer likely lies in the shadow's own quantum properties. If they are not just passive ingredients but active participants in the quantum drama, then understanding them may be the very key that unlocks the next great revolution in physics, forcing us to see the universe not as a collection of things, but as a dynamic and interconnected computation of reality itself. Einstein famously dismissed it as spooky action at a distance, a phrase that perfectly captures the bizarre nature of quantum entanglement. 2 particles can become linked in such a way that measuring the state of one instantly influences the other, regardless of the vastness of space between them. This leads us directly to the 10th riddle. Could quantum shadows themselves be entangled, not just in pairs, but woven into a vast, cosmic web of instant connection? The implications would reshape our understanding of the universe's hidden architecture. If shadows are entangled, it would explain their apparent non-local behaviors, the way their influences seem to connect across galactic distances without any obvious signal passing through the space in between. Insights from laboratory experiments like the Bell test have proven that this spooky action is real. When we scale this ideal up to the entire cosmos, we are faced with a staggering possibility. The entire dark matter halo of a galaxy, a colossal cloud of quantum shadows, might not be a mere collection of independent particles. It could be a single, coherent quantum object, its parts entangled across thousands of light years. This concept of quantum coherence in dark matter is not just a wild speculation. Researchers are now using quantum computers to simulate how such a network of entangled shadows might behave. They program qubits to represent the shadows, linking them with the same kind of quantum rules that govern entanglement. These digital experiments suggest that a coherent shadow network would not clump and collapse under gravity in the same way as a collection of independent particles. It could explain why the centers of galaxies are less dense than some models predict, as the entangled shadows resist being packed too tightly, a phenomenon known as quantum pressure. This leads to a deeply reflective question. If this entangled network is real, could it, in some way, enable a form of cosmic communication? Not in the sense of sending a deliberate message, but as a fundamental channel for information transfer across the universe. The state of one part of the cosmos could be instantly reflected in another, with the quantum shadows acting as the universe's ultimate, instantaneous nervous system. This role as a potential information network forces us to look at the cosmos not as a collection of separate objects, but as a single, interconnected quantum entity, where the shadows are the threads holding it all together. The holographic principle suggests a startling possibility, that our three-dimensional universe might be a projection from a two-dimensional surface at its boundary. Every event, every particle, every star could be akin to a pixel in a cosmic hologram, with the information for the entire image encoded on the distant edge. This leads us to the 11th riddle, a question that touches the nature of reality itself. Do quantum shadows serve as the universe's ultimate hard drive, encoding information about its entire history and acting as a form of cosmic memory? The physicist Leonard Susskind, a pioneer of this idea, has wrestled with the black hole information paradox, the puzzle of what happens to information that falls into a singularity. His work implies that information is never truly lost, but is preserved on the event horizon. Could a similar principle apply to the entire cosmos, with quantum shadows acting as the storage medium? These shadows, being so fundamental, may have been imprinted with data from the universe's first moments. The violent expansion of inflation, the subtle ripples of the first gravitational waves, even the precise initial conditions of the Big Bang itself, could all be recorded in the quantum states of these elusive entities. Think of a still pond after a rainstorm. The surface is covered with overlapping, intricate ripples. Each ripple pattern holds information about where and when each raindrop fell. In this analogy, the quantum shadows are the pond's surface, and the history of the cosmos is the rain. The cosmic microwave background, that ancient afterglow, is perhaps the most famous example of a shadow imprint, a frozen snapshot of the universe's density variations 380,000 years after its birth. But the shadows themselves could hold a far older and more detailed record. The information would not be stored like a book on a shelf. It would be encoded in the relationships between shadows, in their entanglement, in their probabilistic states. Reading this information would be the ultimate archaeological dig, requiring us to decode the universe's most fundamental language. This raises a profound and almost philosophical question. If these shadows remember everything, could we ever learn to retrieve that information? Could we one day look into the shadowy depths and witness the Big Bang itself, not through its fading light, but through the indelible marks it left on the fabric of reality? Such a possibility hinges entirely on the stability of these cosmic scribes, on whether their record can endure for all time. Every particle we consider stable carries a hidden cosmic clock. The proton, for instance, is thought to last for at least 10 to the 34 years, a timescale so vast it dwarfs the current age of the universe. This brings us to the 12th riddle, a question of endurance. Are quantum shadows truly stable over these cosmic timescales, or do they too carry a hidden clock, slowly decaying into other particles and energy? The answer would reshape our understanding of the universe's past and its ultimate fate. Some compelling theories suggest that shadows are not eternal. If they are composed of hypothetical particles like axions, they could theoretically decay into pairs of photons, the particles of light. This process would be incredibly slow and rare, but across the vast, dark oceans of space, the collective glow from countless decaying shadows could create a faint, universal background of radiation, a whisper of light from the dark. To hunt for this, physicists have turned the Earth itself into a shield. In deep underground laboratories, where thousands of feet of rock block out most cosmic interference, experiments are searching for the telltale signs of these rare decays. They monitor immense vats of ultra-pure materials, waiting for a sudden, inexplicable flash of energy that cannot be attributed to any known radioactive process. The signature of such an event is very specific, a precise energy spike that would signal the moment a shadow particle transformed into something we can finally see. Cosmic rays provide another crucial constraint. These high-energy particles, constantly raining down from space, would interact with any decay products floating in the interstellar void. If shadows were decaying at a significant rate, we would expect to see a specific pattern in the flux of these cosmic rays. an anomalous excess of certain particles like positrons, the antimatter counterparts to electrons. Intriguingly, experiments on the International Space Station, like the Alpha Magnetic Spectrometer, have detected just such an excess of high-energy positrons. While not definitive proof, this could be the first faint echo of a vast, invisible decay process happening all around us. So if shadows do decay, what do they become? Their transformation could release energy back into the cosmos, potentially even influencing the expansion rate of the universe over billions of years. A stable shadow universe remains static and dark, but a decaying one is dynamic, its hidden mass slowly converting into radiation, subtly fueling the cosmic engine. This forces us to ask, is the darkness we perceive truly permanent, or are we witnessing a slow-motion fade, a grand transformation of the universe's hidden majority back into the light from which it may have first emerged? Our most accurate map of the cosmos reveals a startlingly lopsided budget. The Lambda CDM model, the standard model of cosmology, tells us that everything we can see and touch, all the stars, galaxies, and planets, account for a mere 5% of the universe's total energy density. About 25% is the invisible mass we call dark matter, while the remaining 70% is the even more enigmatic dark energy, responsible for the accelerating expansion of the cosmos. This is our 13th riddle. What fraction of this immense, unseen budget is filled by quantum shadows? Data from the Planck satellite, which meticulously charted the cosmic microwave background, gives us a precise inventory. The patterns in that ancient light are a forensic report, and they point unequivocally to dark matter making up roughly a quarter of everything. If quantum shadows are the primary constituent of dark matter, then they are not a minor component. They represent 1/4 of the entire universe, a foundational substance that outweighs normal matter by a factor of 5 to 1. Their density is not uniform, however. It clusters in the halos around galaxies, creating localized gravitational wells that dictate how structures form. But it is their average density across the entire cosmos that plays a critical role in the universe's expansion history. The rate of this expansion is measured using distant supernovae, which act as standard candles. The faintness of these exploding stars tells us how fast the universe has stretched over billions of years. Simultaneously, another measuring stick exists, the Baryon acoustic oscillations. These are frozen ripples in the distribution of galaxies, a cosmic ruler imprinted from the early universe. When we combine these measurements with the Planck data, we get a consistent yet deeply puzzling picture. The precise amount of dark matter, the potential shadow substance, is crucial for this consistency. Its gravitational pull acts as a brake, slowing the expansion that began with the Big Bang. But there is a growing crack in this elegant model, known as the Hubble tension. Different methods for measuring the current expansion rate, the Hubble constant, are yielding stubbornly different results. One possibility, though highly speculative, is that the properties of quantum shadows are not quite what we assume. Perhaps their density was slightly different in the past, or maybe they interact in a way that subtly alters the cosmic expansion history. This brings us to a profound reflective question. How does this vast ocean of shadows influence the ultimate fate of the cosmos? Its gravitational pull works to draw the universe back together, while dark energy pushes it apart. The balance between these two titanic, invisible forces will decide whether the universe expands forever into a cold, dark silence, or eventually collapses back upon itself. The shadows are a central player in this cosmic tug-of-war, their silent mass a counterweight to the void's mysterious repulsion. The universe is not just expanding, it is accelerating, a discovery so shocking it earned a Nobel Prize. For decades, we assumed the cosmic expansion was slowing down after the Big Bang, braked by the collective gravity of all matter. Then, Observations of distant supernovae revealed the opposite. The cosmos is flying apart faster and faster, driven by a mysterious repulsive force we call dark energy. This brings us to the 14th riddle. Could the quantum shadows responsible for dark matter also hold the key to this accelerating void? The answer may lie in a forgotten page from Einstein's own work, the cosmological constant. He originally introduced this term as a sort of anti-gravity to keep the universe static. He later called it his greatest blunder, but modern cosmology has revived it as the simplest explanation for dark energy. It represents a constant energy density inherent to the vacuum of space itself. And what is the quantum vacuum but a seething ocean of fluctuations, the very source of our quantum shadows? In this view, the shadows are not just passive masses. Their constant flickering and annihilation imbues empty space with a fundamental energy, a pressure so vast that its gravitational effect is not to pull, but to push. This is where the theories become truly fascinating. Some models, known as Quintessence, propose that dark energy is not a constant but a dynamic field, a fifth fundamental force that changes over time. Intriguingly, this field could be intimately connected to the shadow field. In certain scenarios, what we perceive as separate entities, dark matter and dark energy, could be two different manifestations of the same underlying quantum shadow substance. Imagine a single, universal fluid that behaves like matter, clumping under gravity in some conditions, but acts like a repulsive force in others. The key is its equation of state, a measure of its pressure. For normal matter, pressure is positive. For dark energy, it must be strongly negative. Could the quantum shadows shift between these states? The observational tests for this are incredibly subtle. We look for tiny deviations in the brightness of type 1, a supernova that would signal a change in the expansion history, a sign that dark energy was different in the past. We also scrutinize the large-scale structure of the universe. If dark matter and dark energy are linked, their interplay would leave a specific signature in how galaxy clusters form and evolve. The cosmic web itself becomes a laboratory for testing this profound connection. So we are left with a staggering possibility. The very same shadows whose gravity pulls galaxies together could also be providing the negative pressure that pushes the cosmos apart. Could the invisible architecture that builds the cosmic web also be the engine of its ultimate dissolution? To find out, we must push our inquiry into the most violent and extreme corners of the universe, where the shadows are put to their ultimate test. The crushing gravity of a black hole rips apart the very fabric of space-time. This environment, where the known laws of physics break down, becomes a brutal testing ground for quantum shadows. Our 15th riddle asks how these elusive entities behave at the precipice of a singularity, and whether their presence might resolve some of our deepest paradoxes. Stephen Hawking's revolutionary work showed that black holes are not truly black. Due to quantum effects near the event horizon, they slowly evaporate, emitting a faint glow of particles now known as Hawking radiation. But what role do shadows play in this process? Theoretically, a cloud of quantum shadows surrounding a black hole would be relentlessly pulled inward. Some models suggest they could accumulate in a dense, dark halo, subtly altering the black hole's gravitational field and even its apparent size. Other theories propose that the immense tidal forces could shred shadow particles, with their energy being channeled into the powerful relativistic jets that scream out from the poles of active black holes. The physicist Kip Thorne has explored the complex thermodynamics of these systems, noting that any new form of energy or information would have profound consequences. The infamous information paradox hinges on the question of what happens to the information describing an object that falls into a black hole. If it is truly lost forever, it violates a core principle of quantum mechanics. But if quantum shadows are entangled, or if they can store data as some theories suggest, they might act as a buffer, Information swallowed by the black hole could be transferred to the shadow halo, preserved even as the black hole itself evaporates away. Simulations of accretion disks, the superheated whirlpools of matter feeding black holes, are now beginning to include the gravitational effects of a shadow component. The dynamics change, with the disk potentially becoming more stable or showing different patterns of brightness. Look at the first ever image of the shadow of the supermassive black hole M87 star. While the dark central region matches predictions, there are subtle, unexplained features in the surrounding ring of light. Could these be the gravitational imprints of a dense concentration of quantum shadows, bending the light in ways we are only starting to model? If shadows can modify how a black hole evaporates, or even influence the nature of the singularity at its heart, then they were absolutely critical in the universe's infancy. The early cosmos may have been filled with primordial black holes, and their rapid evaporation or growth would have been dictated by their interaction with the sea of quantum shadows. This hidden dialogue between the darkest objects and the most elusive substance might have set the stage for the first galaxies to form. The universe's rapid expansion during its first moments solved two of cosmology's greatest puzzles. It explained why the cosmos looks so uniform in all directions, the horizon problem, and why its geometry is so perfectly flat. But this inflationary spree did more than just smooth out wrinkles. It acted as a cosmic amplifier, taking the faintest whispers of quantum activity and stretching them into the gravitational foundations of the cosmos. This leads us to the 16th riddle. Did quantum shadows themselves play an active role in this inflationary epoch, their own generation helping to seed the very uniformity we observe? The mechanism is both elegant and profound. During inflation, the fabric of spacetime was a turbulent sea of quantum fluctuations. Pairs of virtual particles, the precursors to our shadows, were constantly blinking in and out of existence. In ordinary circumstances, they would vanish almost instantly, but inflation stretched space itself faster than light, pulling these flickering pairs apart before they could annihilate. Like a piece of taffy pulled in opposite directions, the partners were permanently separated, their brief existence frozen into the macroscopic fabric of the universe. They were no longer virtual. They had become real, a vast and diffuse population of primordial quantum shadows imprinted across the newborn cosmos. The evidence for this process is potentially written in the oldest light we can see. The cosmic microwave background carries a specific pattern known as B-mode polarization, a faint swirling signature in the light that could have been created by primordial gravitational waves. These waves are ripples in spacetime itself, and their most powerful source would have been the violent energy shifts of the inflationary era. Crucially, the same quantum fluctuations that generated the shadows would also have produced a background of these gravitational waves. Their strength is directly tied to the energy scale of inflation. So when experiments like the BICEP array at the South Pole stare at the sky, they are not just looking for waves. They are indirectly probing the birth cry of the quantum shadows. A detection of a specific B-mode signal would be a spectacular confirmation that the inflationary process was powerful enough to create the vast shadow infrastructure we infer today. This deep connection forces a reflective question. Could inflation have worked without generating these shadows? The mathematics suggests the two are inextricably linked. The same quantum jitter that seeded the galaxies is the very process that would have produced the shadow particles. They are not separate actors but different expressions of the same primordial chaos. Without their gravitational pull, the initial seeds for structure might have been too weak, and the cosmic web we see today might never have formed at all. Their quantum origins are not just a detail of their creation, but the very reason for their existence. This debate strikes at the very definition of reality in modern physics. Are quantum shadows fundamental building blocks, irreducible and elementary, or are they collective behaviors that emerge from a deeper, hidden layer of the cosmos? The question of what is truly fundamental has haunted physics for over a century. We once thought atoms were the final level, only to find protons, neutrons, and a zoo of quarks and leptons. Each time we peel back a layer, a new, more fundamental world appears. Quantum shadows could be the final layer, or they could be the smoke from a far stranger fire. One compelling idea is that they are not things at all, but a frothing texture of spacetime itself. In the realm of loop quantum gravity, space is not smooth and continuous. It is granular, composed of tiny, discrete loops woven into a dynamic fabric. Theorist Carlo Rovelli describes these loops as the atoms of space. In this view, a quantum shadow is not a particle moving through space, but an excitation of this very fabric, a specific pattern of vibration in the fundamental weave of the cosmos. It emerges from the geometry of spacetime in the same way a wave emerges from the water it moves through. Another path to emergence comes from the holographic principle and the physics of entanglement. The entropy of a system, its degree of disorder, is often a sign of underlying complexity. The entropy of a black hole is proportional to the area of its event horizon, not its volume, suggesting that all the information within it is encoded on its surface. This hints that our three-dimensional reality, with its quantum shadows, might be a projection from a two-dimensional screen. The shadows we perceive could be emergent phenomena from the entangled quantum data on that distant boundary. They would be no more fundamental than the temperature of a room is to the air molecules within it. Temperature does not exist for a single atom, it is a collective property of their motion. Similarly, quantum shadows might be a collective property of countless underlying quantum bits. A stunning laboratory example of such emergence is the quantum Hall effect. When electrons are confined in a two-dimensional layer and subjected to a powerful magnetic field at near absolute zero, their behavior changes radically. They begin to act as if they are a new kind of particle altogether, with fractional charges and astonishing collective behaviors. Most strikingly, these states are characterized by edge modes, currents that flow effortlessly along the boundary of the material, protected by the system's overall topological order. These edge states are not fundamental particles, they are emergent phenomena, a direct consequence of the collective quantum dance of all the electrons. Could the vast dark matter halos around galaxies be analogous to these edge states, emergent behaviors of a deeper quantum system we have yet to comprehend? This line of thinking leads to a deeply reflective question. If quantum shadows are not fundamental, then what are the true underlying degrees of freedom? What is the equivalent of the vibrating string or the spinning quantum bit from which these cosmic phantoms condense? The answer would revolutionize our understanding of existence, suggesting that the solidity of the cosmos is a grand and persistent illusion. And if their existence is not absolute, but contingent on deeper processes, then perhaps their nature is not constant across the universe. Could the rules governing these shadows change from one cosmic void to the next, creating pockets of reality where the hidden architecture functions by entirely different laws? Our most cherished assumption is that the laws of physics are the same everywhere and for all time. Yet the universe itself is a tapestry of wild variation, from the crushing density of a neutron star to the near-perfect void of intergalactic space. This brings us to the 18th riddle. Do quantum shadows change over time or vary in density across the vast expanses of the cosmos? Could the very properties of this hidden substance be inconstant? Galaxy surveys like the Sloan Digital Sky Survey provide our first clue. They map the positions of millions of galaxies, revealing the cosmic web in stunning detail. By studying the subtle distortions of gravity, we can weigh the dark matter halos around these galaxies. The results show a surprising range of densities. Some halos are incredibly dense and compact, while others are more diffuse and spread out. This is not just random scatter. It suggests that the accumulation of quantum shadows, their ability to clump, might depend on local conditions, on the unique history of each galactic environment. Time domain astronomy adds another layer to this mystery. By monitoring the brightness of distant quasars and supernovae over years, we are effectively taking the pulse of the cosmos. Any slow, subtle drift in the properties of the quantum shadows between us and these beacons could, in theory, imprint itself on the light we receive. If the shadow density along a particular line of sight were to slowly increase or decrease over centuries, it could minutely alter the apparent brightness or redshift of the objects we observe. We are searching for these tiny, slow-motion waves in the fabric of the dark. One of the most direct searches looks for a dipole anisotropy in the dark matter wind. As our solar system moves through the galaxy, we should be plowing through the halo of quantum shadows. If this halo were perfectly smooth, the wind would feel the same from every direction. But if the shadow distribution is lumpy on large scales, we might detect a preferred direction, a slight enhancement in the signal coming from one part of the sky compared to another. Even more provocative is the observed variation in the Hubble constant, the rate of the universe's expansion. Measurements taken in different directions across the sky seem to yield slightly different values. While the cause is hotly debated, one speculative possibility involves the quantum shadows. What if their density is not perfectly uniform across the largest scales? A region of space with a slightly higher density of shadows would have more gravitational pull, subtly slowing the local expansion rate compared to a neighboring void. We would effectively be living in a cosmos with a slightly lumpy expansion rate, a direct consequence of an uneven shadow sea. This forces a profound reflective question. Are these shadows dynamic components of a living, evolving cosmos, or are they a static, unchanging backdrop? If their density can evolve with the universe's expansion, or be shaped by local gravitational dramas, then they are active participants in the story. Their behavior could even provide a missing link to one of physics' greatest enigmas. Could the silent, shifting presence of quantum shadows be influencing what we consider to be the universe's most fundamental and immutable constants? The fine structure constant is a number that seems almost magical in its precision. It governs the strength of electromagnetism, dictating how light interacts with atoms and molecules, and its value is approximately 1/137. If this number were even slightly different, stars might not burn, molecules would not form, and the universe as we know it would be impossible. For decades, physicists have assumed such constants were fixed, locked in at the birth of the cosmos. But what if they are not truly constant? The 19th riddle plunges us into this unsettling possibility. Could the pervasive presence of quantum shadows be subtly tweaking the universe's most fundamental rules? The mechanism could involve a cosmic seesaw with scalar fields. These are invisible energy fields that fill all of space, and their value can determine the strength of a fundamental force. One hypothetical field, called the dilaton, could be directly coupled to the density of quantum shadows. In regions of space where shadow density is high, the dilaton field might shift, causing a corresponding minuscule change in a constant like the fine structure constant. It would be as if the very tuning of the cosmos were being adjusted by its hidden, dark matter component. The evidence for such variation is fiercely debated. Observations of light from distant quasars, which has traveled for billions of years to reach us, allow us to look back in time. By analyzing the absorption lines in these spectra, scientists can check if the fine structure constant was different in the ancient universe. Some teams have reported tantalizing, though controversial, hints of a very slight variation. As the physicist John Webb, a leader in this search, has noted, the statistical significance is not yet conclusive. but the possibility demands our deepest scrutiny. Here on Earth, we conduct exquisitely precise tests. Atomic clocks, which rely on the unwavering vibration of atoms, are our most sensitive monitors. By comparing different types of clocks over years, researchers check for any drift in the constants that govern their ticks. Lunar laser ranging bounces lasers off reflectors left on the Moon by Apollo astronauts, measuring the Earth-Moon distance with millimeter precision. Any slow change in the gravitational constant would reveal itself as an anomaly in the Moon's orbit over decades. Perhaps the most fascinating test comes from a 2-billion-year-old natural nuclear reactor found in Oklo, Gabon. The way this uranium ore sustained a slow, self-regulating fission chain reaction depends critically on the precise value of the fine structure constant at that time. Analyzing the nuclear remnants is like reading a fossilized record of the laws of physics. The data from Oklo strongly suggests the constant has not changed significantly, placing tight constraints on any theory of varying constants. This forces a profound question. If the constants do vary, however slightly, are quantum shadows the invisible hand on the dial? Their widespread gravitational influence and potential connection to fundamental fields make them a prime suspect. The answer hinges on the symmetries these shadows possess. Do they obey the same perfect symmetries we attribute to the vacuum of space? Or could their unique quantum nature break these symmetries in a way that allows the rules of reality to slowly evolve? Exploring their symmetries may be the final key to understanding if the cosmos operates on a fixed set of rules, or if its very laws are part of a grander, more dynamic narrative. Our universe is overwhelmingly made of matter, with almost no antimatter to be found. This profound imbalance is one of cosmology's greatest puzzles, for the Big Bang should have created equal amounts of both. The 20th riddle asks if quantum shadows could be central characters in this drama, their own hidden symmetries or lack thereof explaining why anything exists at all. In the subatomic world, symmetries are fundamental rules. One of the most important is known as CP symmetry, the combined conservation of charge and parity. It suggests that if you replace a particle with its antiparticle and mirror the reaction, the physics should be identical. Yet we know this symmetry is violated, broken in certain rare processes involving quarks. Could quantum shadows participate in their own, much stronger, form of CP violation? If their interactions are not perfectly symmetric, they could have tipped the cosmic scales in the universe's first moments. Particle accelerators like the Large Hadron Collider are actively testing the limits of these symmetries. They smash particles together at incredible speeds, searching for any minuscule deviation from what the standard model predicts. The goal is to find a new source of CP violation, one powerful enough to explain the matter-antimatter asymmetry. This is where the shadows enter the picture. Many theoretical models of baryogenesis, the process that generated the excess of matter, now involve a shadow sector. In these scenarios, the quantum shadows are part of a hidden realm with its own forces and particles. In the hot, early universe, these shadow particles could have decayed, and if their decay processes violated CP symmetry, they would have produced a tiny surplus of matter over antimatter in the visible sector. It would be a leak from the shadow world into our own, a cosmic favoritism written into the laws of physics by the very entities we cannot see. One of the most sensitive searches for such effects is the hunt for the neutron's electric dipole moment. A neutron is electrically neutral, but if it has a slight internal separation of positive and negative charges, it would possess a tiny dipole moment. The standard model predicts an almost immeasurably small value, but many shadow sector models predict a much larger one. Experiments use ultra-cold neutrons, suspended in magnetic fields and observed for precession, to look for this telltale signature. Finding a larger than expected dipole moment would be a direct signal of new physics, potentially pointing directly to the CP-violating nature of quantum shadows. This leads to a deeply reflective question. Do these shadows hold the key to why we exist? Their hypothetical role in breaking a fundamental symmetry might not just be a minor detail of particle physics. It could be the very reason the universe is filled with galaxies, stars, planets, and life, rather than having annihilated itself into a featureless sea of pure light. The search for their symmetrical nature is therefore a search for our own cosmic origin story, pushing us to ask if the next great discovery in physics will come not from what we can see, but from the profound and hidden asymmetries of the quantum dark. The possibility that quantum shadows are not just particles, but bridges is perhaps their most mind-bending feature. In particle physics, there exists a theoretical landscape known as the Hidden Valley, a secluded realm of particles that rarely, if ever, interact with our own. Quantum shadows could be the residents of this valley, and more importantly, they could be the messengers, the only fragile link between our world and this hidden one. They might not be the final destination of our search, but the gateway itself. This idea finds a stunning visual in string theory's brainworld scenarios. Imagine our entire universe, with all its stars and galaxies, is a single three-dimensional membrane, or brane, floating in a higher dimensional bulk. The quantum shadows we detect could be particles that are actually moving through these extra dimensions, their gravity leaking into our brain while they themselves remain forever out of sight. They are not in our world, but their shadow is cast upon it. How could we possibly detect such a phantom gateway? In particle colliders like the Large Hadron Collider, scientists look for events with missing energy. When protons are smashed together, the total energy and momentum before the collision must equal the total after. If a significant amount of energy simply vanishes, it could be a signature that something invisible was created and carried that energy away, perhaps into a hidden sector or an extra dimension via a quantum shadow portal. The data is scoured for these energy ghosts. One of the most persistent anomalies pointing towards such a portal involves the muon, a heavier cousin of the electron. Its magnetic moment, a property known as G2, has been measured to be slightly different from what the standard model predicts. This tiny discrepancy could be explained if virtual quantum shadows are popping in and out of existence around the muon, subtly influencing its behavior with forces from a hidden sector. These shadows would be the mediators of a conversation we can barely hear. So what truly lies beyond the shadow veil? It could be an entire zoo of new particles governed by forces completely unknown to us. It could be the source of dark energy, or the reason for the matter-antimatter asymmetry. The quantum shadows are the tantalizing threads we have managed to grasp, threads that may lead us into a reality far vaster and stranger than we ever conceived. This gateway role suggests they were not passive bystanders in cosmic evolution, but active architects, their connections to other dimensions potentially shaping the very laws that allowed our universe to form. From the first searing moments to the galaxies we see today, quantum shadows have been a constant guiding hand. Their influence is woven into the entire timeline of cosmic evolution, a silent partner in every major event. During the era of Big Bang nucleosynthesis in the first few minutes, the universe was a fusion reactor, forging the first light elements like hydrogen and helium. The gravity from the already present quantum shadows subtly shaped the density of the primordial soup, influencing the rate at which protons and neutrons could find each other to form these atomic nuclei. This set the initial chemical composition for everything that would follow. Later, during recombination, when the cosmos cooled enough for electrons to combine with nuclei and release the cosmic microwave background, the shadow's gravitational wells were the molds into which this new neutral gas settled. Their architecture predetermined where the first stars would eventually ignite. Cosmological simulations are our time machines for testing this grand narrative. When physicists run models that include the gravitational pull of these cold, weakly interacting shadows, the universe that evolves is stunningly accurate. We see filaments of dark matter form first, a vast cosmic skeleton. Then, ordinary baryonic matter, the stuff of stars and planets, flows along these invisible rivers, pooling at the intersections to create galaxies. This is the integrated effect, a feedback loop where the shadows provide the gravitational potential, and the normal matter falls into it, eventually forming stars whose radiation and supernova explosions can, in turn, heat and redistribute the surrounding gas, subtly altering the very shadow halos that birthed them. There were entire cosmic epochs where shadows were the undisputed dominant force. Before the first stars lit up during the Dark Ages, the universe was ruled by their gravity alone. Then came reionization, a dramatic transition when the first galaxies and quasars flooded the cosmos with enough ultraviolet radiation to tear electrons away from atoms once again. The timing and pattern of this reionization were dictated by where these first luminous objects could form, and that was entirely guided by the underlying distribution of quantum shadows. They provided the stage upon which the lights of the universe could finally switch on. This deep, intertwined history forces a humbling reflection. Would the complex cosmos we inhabit, with its stars, planets, and potential for life, even exist without the subtle, persistent pull of these quantum shadows? Their silent gravity was the essential scaffold, the unseen architect that made a structured, life-friendly universe possible. As we look to the future, our ability to detect their finer details will determine if we can finally read this hidden chapter of our own cosmic origin story in full. The next generation of telescopes and detectors is being built with one primary goal: to illuminate the dark. These are not incremental improvements but revolutionary leaps in sensitivity, designed to capture the faintest whispers of the quantum shadow world. The James Webb Space Telescope peers into the infrared, allowing us to see the very first galaxies as they ignited. Their formation patterns will provide a stringent test for how quantum shadows guided the earliest structure. The European Space Agency's Euclid mission is a dark universe detective, mapping the shapes of billions of galaxies to trace the subtle distortions caused by the gravitational lensing of dark matter filaments. It will create the most precise map yet of the shadowy cosmic web. On the ground, the square-kilometer array will use thousands of radio antennas to survey the sky, detecting the neutral hydrogen gas that traces the distribution of matter in the infant universe, revealing how shadows and normal matter fell together over cosmic time. As astronomer Priyamvada Natarajan has expressed, we are entering a golden age of multi-messenger astronomy, where we combine data from light, gravitational waves, and potentially even neutrinos to triangulate the properties of the dark sector. The specific signals are incredibly subtle. We will look for gamma-ray signatures from the annihilation of shadow particles in dense regions like the galactic center. We will search for minute timing variations in pulsars, the universe's most precise clocks, caused as their radio beams travel through ripples in the shadow sea. We will analyze the delicate patterns in the cosmic microwave background with even greater precision, hunting for the unique imprint left by shadows that interact with photons, no matter how weakly. The timeline for these revelations is now. Data from these observatories is already flowing in, with major results expected within this decade. Their combined sensitivity will probe regimes of interaction strength and particle mass that have been completely inaccessible until now. A particularly illustrative search involves primordial black holes. If certain types of quantum shadows were to clump extremely densely in the early universe, they could have collapsed to form these ancient black holes. Projects like the Subaru Hyper subprime CAM are scanning the sky for the telltale flashes of gravitational microlensing, where a primordial black hole passes in front of a star, briefly magnifying its light. Finding a population of these objects would be a stunning indirect detection, a shadow proxy revealing itself through gravity's lens. After decades of searching, will the next 10 years finally deliver the truth? Or will the shadows only retreat further into the darkness? The answer likely hinges not just on our tools, but on the theoretical frameworks that guide where we point them. Every theoretical model of quantum shadows makes a distinct set of predictions, a series of falsifiable claims that can be confirmed or shattered by data. Supersymmetry, for instance, predicts a whole shadow zoo of superpartner particles, with specific mass ranges and interaction cross-sections that the Large Hadron Collider could potentially produce. If no such signatures appear at higher energies, the theory must be revised or abandoned. String theory, with its extra dimensions, forecasts subtle imprints on the cosmic microwave background, specific patterns of polarization that differ from those predicted by simpler inflationary models. It suggests that the gravitational wave background of the universe, the primordial hum from the Big Bang, should have a unique spectral shape, a fingerprint of the vibrating strings from which shadows may be composed. The theorist Nima Arkani-Hamed has emphasized that the next decade of observation will be a brutal arbiter, a period of winnowing where entire families of ideas will fall away. This process relies as much on null results as on positive detections. When an experiment like Xenon 1T reports no signal, it doesn't mean nothing was learned. It carves away vast territories of theoretical possibility, telling us precisely what the shadows are not, forcing the models to become more precise and more daring. Proposed tests are pushing into incredibly subtle realms. Atomic interferometry uses the wave nature of atoms to detect the faintest gravitational tugs of a passing shadow cloud. Quantum simulations on advanced computers can model how entangled networks of shadows would evolve, providing a digital universe to compare against our own. A prime example is the global hunt for Axions. If these hypothetical particles are the shadows, they could convert into microwave photons in the presence of a strong magnetic field. Experiments like ADMCS use tuned superconducting cavities, essentially high-tech radio receivers, to listen for this specific whisper from the dark. Finding an action would not only solve the dark matter riddle, but also resolve a major puzzle in particle physics concerning the strong nuclear force. Its discovery would validate one entire pathway of thought, while its continued illusion would push us toward ever more exotic possibilities. As we stand at this threshold, a reflective question emerges. Which of these intricate theoretical architectures will withstand the coming confrontation with data? The answer will tell us not just what the shadows are, but how deeply we understand the fundamental laws of reality. This search for their definitive identity inevitably leads to a final, overarching wonder about their place in the cosmos. Could these quantum shadows be a universal constant, a necessary feature of any conceivable universe? Our entire model of cosmology rests on a single, powerful assumption: the cosmological principle, which states that the universe is homogeneous and isotropic when viewed on a large enough scale. This principle must extend to its dominant component, the quantum shadows. If they are the dark matter, then their fundamental nature should be the same in a distant quasar as it is here in our own Milky Way. Yet the cosmos loves to test our assumptions, and the 25th riddle asks if these shadows are truly identical in every galaxy and cosmic environment. The evidence comes from comparing wildly different celestial objects. Take the faint, diffuse dwarf galaxies that orbit larger ones. They are so dominated by dark matter that their visible stars are like a few scattered lights in a vast, invisible ocean. The behavior of the shadows in these systems, inferred from the motions of their stars, aligns perfectly with what we see in the immense halos of giant spiral galaxies like Andromeda. The same cold, collisionless substance seems to be at work, governing the dynamics of both the smallest and largest galactic structures. A stunning illustrative case is the Fornax cluster, a massive collection of galaxies over 60 million light-years away. By mapping the gravitational lensing within this cluster, astronomers have weighed the total dark matter, both within the individual galaxies and, crucially, in the space between them. This intracluster shadow substance behaves with the same consistency, its distribution and density following the predictions of models that treat it as a universal, invariant particle. The shadows in the crowded core of the cluster appear to be made of the same stuff as those in the isolated voids on its outskirts. This consistency is what allows our cosmological models to work at all. If the properties of quantum shadows varied from place to place, if they interacted more strongly in galaxy clusters or possessed different masses in elliptical galaxies, our entire predictive framework would crumble. The cosmic microwave background would not match our observations, and the large-scale structure of the universe would look fundamentally different. The shadows seem to play by one set of rules everywhere we look. But why should this be? It points to a profound origin story. Their uniform nature suggests they were created in a single, universal process in the very first instance of the universe. Their properties locked in during that primordial forge and remaining unchanged for billions of years. This leads to a final, deeply philosophical reflection. Is the concept of a quantum shadow a universal constant, a necessary and identical ingredient in any conceivable cosmos? Or is our universe simply one specific realization where this particular type of shadow happened to form? The answer determines whether we are discovering a fundamental truth of existence, or merely describing the local bylaws of our own cosmic neighborhood. The age-old question of what is truly real has haunted philosophy for millennia. Quantum shadows force this question into the stark light of modern science, challenging our most basic definitions of existence. If something can shape galaxies, dictate the fate of the cosmos, and yet remain forever beyond our direct perception, in what sense can we say it is real? The philosopher of science Bas van Frossen has argued for constructive empiricism, suggesting that science aims only to give us theories that are empirically adequate, not to describe an unobservable reality. From this view, quantum shadows are merely a useful fiction, a powerful model that saves the phenomena we see. Yet their gravitational pull is anything but fictional. Their influence is as real as the ground beneath our feet, even if their substance is an eternal mystery. This tension lies at the heart of scientific realism. Do our best theories truly describe the world as it is, or are they just incredibly effective tools for prediction? The shadows exist in a liminal space, defined entirely by their mathematical description and their gravitational effects. Mathematics becomes the primary language for describing an entity we may never touch or see, raising the question of whether the equations are the ultimate reality, and the physical world is just a manifestation. This echoes Plato's ancient allegory of the cave, but with a profound quantum twist. We are not prisoners watching shadows cast by a fire. We are beings within a reality that is itself a shadow, a probabilistic projection cast by a deeper, more fundamental existence we can only infer. The galaxies we map and the particles we collide are merely the flickering images on our cave wall, while the true sources, the quantum shadows and the structures from which they emerge, remain hidden in a brighter, more complex dimension of reality. So are we seeing only shadows of a deeper truth? The very persistence of these 26 riddles suggests that our current reality is a partial picture, a magnificent but incomplete draft of a cosmos whose full nature is written in a language we are only beginning to decipher. This humbling realization does not diminish our quest, but elevates it, transforming the search for quantum shadows from a technical puzzle into a fundamental exploration of what it means to be, to know, and to observe in a universe that may be far more mysterious and interconnected than it appears. These 26 riddles are not isolated mysteries. They form a single, intricate web where each question tugs on the threads of all the others. The profound challenge of detecting a quantum shadow is directly tied to the theoretical frameworks we use to describe it. If string theory is correct, our detectors must listen for vibrations from hidden dimensions. If loop quantum gravity holds true, we are sensing the hum of spacetime itself. The shadows refuse to be confined to one branch of science, demanding a synthesis of cosmology, particle physics, and quantum information theory. This reveals our first overarching theme. Quantum shadows are not merely components of the universe. They are potentially the unifying concept that bridges its largest scales and its most fundamental laws. Insights from wildly different disciplines are beginning to converge. The physicist studying the Casimir effect in a lab and the astronomer mapping gravitational lensing in a distant cluster are ultimately probing the same elusive substance. Their separate puzzles are pieces of a grander picture. Consider how the inflationary origin of shadows connects to their role in cosmic structure. The same quantum jitter that seeded the first galaxies also generated the primordial gravitational waves we now hunt for at the South Pole. Solving the riddle of their composition could simultaneously explain the matter-antimatter asymmetry, revealing how a hidden asymmetry in the shadow sector gave us a universe of matter. This cascade of understanding is the great promise of this field. A single breakthrough in one area, like the direct detection of a shadow particle, would send shockwaves through every connected riddle, constraining theories of quantum gravity and clarifying the universe's ultimate fate. This interconnectedness makes interdisciplinary research not just helpful, but essential. The cosmologist's map of the cosmic web and the quantum computer scientist's simulation of an entangled network are two different languages describing the same hidden architecture. Their collaboration is what will ultimately translate the shadow's silent script. So, will a grand unified theory of shadows emerge from this synthesis? One that seamlessly explains their birth in the Big Bang, their ghostly nature, and their guiding hand across 14 billion years. Such a theory would not just solve these 26 riddles. It would fundamentally rewrite our story of cosmic evolution, placing quantum shadows at the very heart of reality's grand narrative. Our journey through these 26 riddles has taken us from the smallest flicker in the quantum vacuum to the grandest structures in the cosmos. We have explored their ghostly nature, their silent gravitational hand, and their potential role as cosmic architects, and even as gateways to other realities. Each unanswered question represents a frontier where our current understanding meets the profound mystery of the dark universe. These are not merely technical puzzles for physicists in lab coats. They are fundamental challenges that invite every one of us to look up at the night sky and wonder about the deeper, hidden workings of existence. The pursuit of these shadows is far more than a scientific endeavor. It is a fundamental human quest to understand our place in a reality that is largely invisible. As our tools grow sharper and our theories more daring, we must remember to keep looking into the darkness, for it is often in the deepest shadows that we find the most illuminating truths about cosmic evolution. Tell us which of these 26 riddles captured your imagination the most. Was it the possibility of entangled cosmic networks, the search for a hidden portal, or the question of their ultimate stability? Share your thoughts in the comments below, and subscribe to join us on our next deep dive into the great mysteries of